Okay, so let me repeat that very quick. Basically, on the next part, we're going to finish the calculation, but on the next part, we're going to see if we're going to solve the problem using the ideal gas relation, and we're discussing that in here it's a mixture, so it's water and gas. Here is just gas or vapor, and here is just liquid. So the ideal gas substance means that if a substance is within one state, the property should not change much, okay, if it doesn't change state. So the farther away you are from this line here, probably the better the assumption is for the ideal substance, and can be farther away on any direction. But the closer you get, probably the ideal substance assumption is not good and can definitely not be applied when you are on the mixture area, no? Because the substance is at two different states at the same time. Okay, so last time we did this problem. Doesn't look like we finished the numerical application, but we did this problem using tables. So the difficult part, again, was to find the location of 1 and 2. And in order to do that, we needed to use the table. So we knew the temperature, T1, and we went and checked on table A3E. We found that the saturation temperature, which water at this pressure will start boiling, was 503, no? If our temperature given to us was 550, that means that we already passed the state of boiling and the substance is in the gas or vapor state. All right? Then we see over here, we knew that this process between 1 and 2 follow a polytropic relation. We knew P2, and I think using this with the ideal gas, using the polytropic relation, we were able to find V2. So now we knew two things at this stage. We knew P2 and we knew V2, no? All right? So by looking at the V2 value, what happened if we know the pressure? If the V2 value that we calculated was lower than the VG, was between the VG and the VF, it will be in the mixer area. If it was lower than the V fluid, it will be in this case. But in our case, the V2 was higher than the V gas, no? The value over here, so we concluded that it was on the gas state. That's probably what we did. So you see V2 higher than VG, so it's on the gas state. So we did how to do an interpolation to find the U, and basically then at the end, we went back to the principle of thermodynamics. So the Q over M was equal to the change in internal energy plus the amount of work done by the polytropic process, all right? So we wrote down the equation. We needed to find the work over M for the polytropic process, and this was the relation we had. So, all right, let's do the calculation and see what happens. All right, so page 53, keep that page over here. Let's say, so let me rewrite it very quick. Q over M equal U2 minus U1 plus 1 over 1 minus K, P2 V2 minus P1 V1. Okay. So let me go back to all the calculations we did and see what we have. So we know that P1 is 700 lbf in square. P2 is 3000 lbf inch square. Then be careful here, we calculated that V sub 2 to be equal to 0.293 cubic feet per pound. Oh, V1 we found to be 0.728 cubic feet per pound. U1 1,149 BTUs LB, and U2, let's see what I have, U2 to be equal to 1382 0.6 BTUs LB. All right, so guys, you're going to need this space. So let's write down the relation BTUs to foot-pound forces. We know that 1 BTU, we're going to need that one, is equal to 778.17 foot-pound force, okay? So I think that's all we need. So this page, I told you to have it with you all the time. So here we go. All right, so over here, to save some time, we're going to do that in 2 steps, and you can do the calculations for me. So here, this will be equal to what? Q over M will be equal to 1382.6 minus 1149. Can somebody give me that value over here, that quantity, please? Now let's do the second one. So here is where we need to be a bit more careful. Plus 1 minus, I think K is 1.6 times. So do we need to do change of units here? I'm not going to have space. So guys, all right, so P2 is what? Is 3,000. But this is pound force inch square. All right, so 3,000 times V2, which is 0.293, minus 700 times 0.728. All right, but here be careful, because what do we need to have with this one, with the second one? First thing we need to do is to transform what? Those inch square over here for the pressure into square foot, no? Okay, so this is divided. So what do we have? We're gonna have 12 square inch square equal to 1 foot square. I know it's 144, you probably know that. And then what were the units for the internal energy? BTUs per pound, no? So we need now to transform all this one here, the foot LBF, into BTUs. So if you remember, this is the pressure would be LBF divided by foot square times foot cube, no? Yeah? So this will give us times 1 BTU divided by the 778.17 foot LBF. So now if you want, you can give me the overall result. Okay, so the answer is 119.5. Now we're going to do this with the ideal substance assumption. I'm going to pause a second because I'm going to see if they have some values on the tables. Okay, let's do 355 or 356. Let's do 355 because I see this is a quality factor, okay? And I think it's important that we deal with the quality factor. This is a problem. So what you need to do, as I read the problem statement, what I'll be looking, for example, at on an exam, or take-home exam, on an in-class exam, but it's not going to happen, will be what? Water in a piston cylinder assembly. As soon as I read piston cylinder assembly, what do? I sketch a piston, because that's basically going to tell me that we are dealing with a closed system where the mass will be constant, and we know this is water. All right? So water in a piston cylinder assembly, initially at a temperature of 99.63. So that So I think that's actually the boiling temperature. So T1, 99.63 degrees Celsius. And equality, so of 65% is heated at constant pressure. So we add heat over here, and we know that this is constant pressure. Okay? I mean, is that really necessary that they tell us it's constant pressure? What is one of the properties of a free piston? Is that if you heat this, this is going to move freely up, no? So the pressure will be constant. If you cool it, it's going to go down, but the pressure will still be constant. So it's heated at constant pressure to a temperature of 200. So T2 equal to 200 degrees Celsius. Now the work, so we need to be careful here. If the work during the process is 300 kilojoules, so work if the work during the process is 300 kilojoules positive, so positive work for the book is work done by the system, no? If I remember right. So that means that there is 300 kilojoules going out. Determine the mass of water, so we need to find the mass of water, the heat transfer in kilojoules, so Q in kilojoules, the mass of water in kilograms, change in kinetic and potential energy can be neglected. So you can say change in kinetic energy equal change in potential energy equal to 0. But here they don't give us the initial pressure. Okay. Let's go over here. So this is the data we have. So let's see what happened. So what does that mean? Here that means if we deal with water, and let's say we are with this figure, so which one you want to use, the TV or the PV? I like to use I'm going to use the TV over here, because the TV, what do you have? You have lines of constant pressure, correct? Yeah? Okay, remember I told you could bring that page where you have the TV and the PV diagrams and the equation with the quality factors. I remember, let's see if I have it right here. With the properties is that page over here. Okay, remember with the qualities and these figures over here, that's what we need to understand. All right, so here we are. All right, so what do we know? We know that we go through a line of constant pressure, but we don't know what it is. Okay? But what do we know? Where is state 1? It's going to be somewhere over here because it's a mixture, no? 65% is in gas state, so let's say it will be somewhere over here. It should be 1. In this state, we know that X1 is 65%. All right, and we know that T1 over here, I think that's actually the temperature for 1 atmosphere, but T1 equal 99.63. So can we go to the tables of water in function of the temperature and see what would be the pressure for that temperature? Because we know that the temperature all along this line here is the same one, no? When you boil water, as long as the water is boiling, remains the same temperature, okay? Boiling temperature of water is 100 degrees Celsius, no? Yeah, okay. So if we go to the tables, so hopefully now we can go to the tables. So let me close this one. Close this one. All right, let's come here. Let's go back to the tables. Okay, let's see the top stuff on top disappears. All right, there we go. So let's go back to the tables here. I want table 22, so let me go up. This is going to be table A2 or A3. This is table A4, A15. All right, let's get there. So let's see, this is A4. Here we have the temperature. So this is the one we want, temperature A2. Okay, so 99.63, then I'm going to have it. We can interpolate, but I think this is actually the boiling temperature. So let's go to table A3 and see what happened. Table A3, and I think you see 99.63. This is like the ambient pressure, no? Which is 1 bar in this case. So write down over here from table A3. At T equal 1 bar, T saturation equals to T1, which is equal to 99.63. Okay, and you see here 1 bar is 100 kilopascals. Basically right here. So from this means what? From here we can write down that then P1 equal to 1 bar equal to 100 kilopascals. All right, so P1 here equal to 100 kilopascal, which will be also P2. Okay, they tell us the process is constant pressure. So what would be the state 2 if we know the temperature is 200? If this is 200, what should be the state? It should be gas or vapor. So it should be 2 over here. Okay? So basically, if I needed to spot the process, you first go from here to here, and then from here to here. So I don't know how you want to call this point here. Let's call this point here A, okay? So, out of this figure, all right, let's try not to put too much on the figure. But again, this could be V, this could be also the internal energy, no? Whatever we want to find on the table. All right, so now, from the table at P equal 1, so from table A3, we can also find what? We can also find what is V fluid over here and what is Vg over here. Okay? So this is the saturation volume. And this would be here the saturation gas, and this would be here V1. So table A3 at 1 bar, what do we have? We have V. Let's first start by V gas. V gas equal to what? 1.694. Okay, what takes more space? Gas or liquid water? It is gas, no? So that means that the quantity F sub, they call here F, V sub F, should be smaller than this. So what should be the quantity then? It's 1.0432, what? 10 to the minus 3, no? So that means that this quantity has already been multiplied by 1,000. So you need to do 10 to the minus 3 because otherwise it will be bigger than this one. It makes no sense. Okay, since we are here, let's do the same thing for the internal energy over here. Take U sub F. So U sub F is 4017.36. U sub gas is 2506.1. Okay, I think that's all we're going to need for this. All right, let me go back over here. Okay, I think I'm going for the Q over M. I'm still not solving for, okay, yeah, let's solve. I'm solving for everything at the same time. Okay, so from the page I gave you before, that I will just spend before. What about the quality factor? Properties of substances. What is the relation? Remember, this will be V1 would then be V fluid plus X1, V gas minus V fluid. So we have from this equation, all right, V1 will be equal to V fluid plus X1 times V gas minus V fluid, which will give us what? Let's do the numerical application. Will give us V fluid is 1.0432 10 to the minus 3 plus what is X1? Is 65%, meaning that is equal to 0.65 times V gas, so 1.694 minus 1.0432 10 to the minus 3. So what do you get for V1 over here? And this should be, what should be the units for this? Sorry, this is cubic meters per kilogram. Okay, so please do the calculation for V. All right, so they give me the result here has been 1.1 cubic meters per kilogram. Here, let's do the same thing, but let's find out what will be U1, okay? So basically, we do exactly the same thing, but for the internal energy. So we'll have U2, no, U1, sorry, will be equal to U sub F plus X sub 1, UG minus UF, which will be 4017.36 plus 0.65 times 2506.1 minus 417.36. And this will give you U1 in kilojoules per kilogram. All right, so just trying to do everything I can here. So next thing will be what? All right, so all right, on this figure, okay, V sub A will be equal to what? V sub A should be equal to V sub G, no? Yes? We have V sub G, and we know that is, we had it here, is 1.694. Okay. Okay, and similarly, we can say U sub A will be equal to U sub G, which is 2,506.1. Okay, so guys, what I'm doing, maybe you don't see it, but I'm just following the line. No? I go from 1 to A, I try to find everything, and now I go to point 2, no? Okay, so what do we know at point 2? We need to know two things in order to find the values. Do we know two things at point 2? Do we know the temperature? What else do we know? The pressure, no? It's constant pressure. So at point 2, or at state 2, we know the pressure, so P2 equal to P1 equal to 100 kilopascals, or which is 1 bar. I don't know what will the tables give you. And we know that T2 is 200 degrees Celsius. All right, what else do we know? The state. What is the state? We know is vapor or a gas, no? So it should be under superheated vapor tables. So that, what does that mean? If we know the state, we know we're gonna have to go to table, I think is A4. What is the table that gives you the state? I think it's table A4. But again, you could do it from this one. At 1 bar is 99.63. We know we have 200. So we know it's gonna be vapor or, so let's see, table A4. This is superheated water, which basically means vapor or gas. So we have here pressures, so it's in bars. So we are here at 1 bar, which is 100 kilopascals. What is the temperature? They put here 99.63, no? Yeah? So this is the saturation temperature. But in our case, what is the temperature we're dealing with is 200. So meaning that we need to look at this line over here. So the first one will be V. So one will be U, no? So from table A4, we can find that V2 is equal to 2.172, and U2 will be 2,658.1. All right, so write down over here. So from table A4 at P equal 1 bar, T equal 200 Celsius, we have that V2 and U2 are equal to so V2 is 2.172 cubic meters per kilogram, and U2 is 2,658.1 kilojoules per kilo. This is a good problem. So far I like it. Maybe I won't like it later on, but so far I like it. All right, so basically right now, the total work done doing this process will be equal to what? To the work done between 1 and A, which will be a constant pressure, no? And then here between A and 1, so this is a good question. I guess they assume this will be a linear relation, or they're just going to assume PV equal to constant on this one. Okay, so let me. All right, guys, so here, this is to me, I think the base figure to see what's happening here, but we need to be careful here because really, these figures might be a little bit confusing. Between 1 and 2, what do we know? The pressure is constant, no? Okay, so if I needed to do another figure for the work, what would we know? If this is the pressure, we know the pressure is 1 bar or 100 kilopascals, and is what? Is constant between 1 and 2, no? Yeah? So this will be V1, this will be V2. So really, we could do it graphically, but what is the definition? At constant pressure, the work will be the area under the curve. Correct? We know the definition of work is what? Is integral of P dV. Okay, for the total volume. Or we know this could be, we can write this as work over M will be equal to the integral of P d lowercase v, which is the specific volume. Specific volume is volume over mass, per unit mass. All right, so if I go to the next page, this will mean what? Work over mass equal to, let me write it here, PdV between V1 and V2. So basically we're going to have work over mass equal to P V2 minus V1. So from this equation now we can solve for the mass. The mass will be equal to the work divided by the pressure V2 minus V1. Okay, so over here we need to do the numerical application, but let's be careful with the units. So we know the work is given to us to be equal to 300 kilojoules. P is what? Is 100 kilopascals. Okay, we know that V1 is equal to 1.1 cubic meters per kilogram. V2 is 2.172 cubic meters per kilogram. Again, we might need to use the relation, or let's see if I have it here. No, looks like the one of the units. We can go back. There we go. So units. That's why you need to have this with you. I don't think we need this one, but what is 1 joule? 1 joule is 1 Newton meter, no? Okay. All right, so okay, so what should we do here to units? This is kilopascal, so I don't think we need to do anything, no? Very good. So this will give you M will be equal to what? 300 kilojoules divided by 100 kilopascals. So 1 joule we say is Newton meters. 1 Pascal is Newtons meter square, no? Yeah? Times V2, which is 2.172 minus 1.1, and this will be cubic meters per kilogram. So basically we have these cubic meters will cancel out because you have meter squared times meters. And now the Newton will cancel with the Newton, so we only left with kilograms. Okay? So what do you get if you do this calculation? So units are okay. All right, so we're going to get here 2.8 kilograms. All right, so let's go back over here and find a way to find what is the amount of heat that is provided into the system in order for this process to happen. To go from a mixture of water to take water at 200 degrees Celsius, we need to put heat, no? Okay? All right, so here we use the first principle. Of thermodynamics, which is what? Heat minus work equal to the change in energy. If we neglect the kinetic and potential energy, this is going to give us what? Q equal to the work plus the change in internal energy, no? Okay? And now this is the capital U's. What is the difference between the capital and lower cases? Lower cases are values per unit mass, no? Okay? And these are not unit mass. So we could say that Q will be equal to W plus M lowercase u, lowercase u sub 1. Okay, so finally, if we do the numerical application, we're going to have Q will be equal to what? 300 kilojoules. plus the 2.8 kilograms times the U2. Did we calculate U2? Yes, U2 is 2,658.1 minus U sub 1, which is 1775, and this was in kilojoules per kilogram. So you see the units work. So we get Q in kilojoules. So 2,272, let's say 0.6, okay? Just to go over. Point what?
2,700.
Oh, how much is 2,000?
700.
2,772? Okay, sorry for that. Okay, guys, so we don't have time to do another problem. So what I want to say is that these problems, and I don't want to say that they're not difficult, but mathematically in thermodynamics, there's nothing difficult. It's all multiply, divide, and addition, subtraction, no? Okay? But what is the most important part of the whole problem? Here, no? I mean, if you don't have the figure, at least me, if I don't have the figure, I'm not going to say it's impossible, but it's extremely hard to do the problem because you don't know where you stand.
Can you explain how you do that?
This one?
Yeah.
Okay, so you have two choices to do, okay? When you do this type of figure, let's see if I have here. Here we go. Remember I said that you can either choose the TV diagram. If you do the TV diagram, you're going to go through lines of constant pressure. So in this case, what I like the TV diagram. Don't ask me why, but I'm more fond of that one than the other one, because if the process they told me that is a constant and the temperature changes, I know everything is going to go through this line. Okay? The other choice you have is, instead of the TV diagram, is the PV diagram. And in this case, if you have the PV diagram, what would be the lines coming? You have lines of constant temperature. Okay? So you can choose either one. But basically, how did I do this one? Since I like more this one, I draw this general curve, which is my blue one, and I draw one line of constant pressure. Okay? Now, I know on the left side of this curve, I know it's liquid. On the right side of this curve, I know it's vapor or gas. And in the middle is a mixture. Okay? So if I go back to our problem, what do they give us in our problem? What do they say about state 1? They give us the temperature, and if they give us the quality factor, what does that mean about the state? We know right away that the state is going to be a mixture, no? So we knew right away that was going to be here in the middle, somewhere in the middle, no? in that area. Okay? So then what did I do? This line here, I didn't know the pressure, but I know the temperature. The temperature is 99.63. We check on the table A3, and that means that at that temperature, this line of pressure, so this line, straight line, is 1 bar or 100 kilopascals. Okay? That's why I say without the figure, it's impossible. All right. So next, what do? We know that the cell temperature is 200. So we know that the process is constant pressure. So we know we go along this line, no? So if the temperature is 200, that means that the state is going to be on the superheated or vapor region. Okay? So I know we're going to be somewhere over there. Now that we know we are here, I know that I need to go to the tables for superheated vapor, which is table A4. So from table A4, I'm able to get the value for V sub 2 and U sub 2. Okay? The only thing that this figure wasn't good is to see what is the work. Okay? The only thing that the other figure was actually better for this one is to see what is the work, because what do we know between 1 and 2? The pressure is constant. So it's a pressure constant process, no? From 1 to 2. That's why I sketch the other figure, this one here, and say, okay, you need to realize that between 1 and 2, the process is constant. So what is the work done by a constant pressure process? Basically, we know that it's just going to be equal to P, so the area under the curve, P times V2 minus V1, no? Which is what the relation gave us. What is that page? Here we go. No. It's this one here, sorry. So we knew that then the work is equal to P2 over V1, and from this expression, then, I mean, this is nothing to do with the figure, we're able to solve for the mass. So does that answer your question? Yes?
I also want to make sure I understood for this particular problem, because there's constant pressure, do we need B sub A and B sub A?
No, we did not need it. No, we did not need it. Use of A. I thought we needed it because when I was doing the problem, I thought we we're gonna have to use one expression between, yes, 2 different works. But you see, I was putting too much. I thought we we're gonna have to use one expression between 1 and A and another one between A and 2. But since it's constant pressure, we can use the same one. Okay? All right, so guys, practice, start the homework about this, and if you have any question, come and ask me, and please do the homework. Don't do round-off in the middle steps.
So the homework says that it's part of a homework module with it.
All right, so let me end this, and I look at it right now. So hopefully we